might as well source this. Now let's see if it will. No, it actually asked for the password. So why? Because I am SSHing from RNACam. Good. So what I need to do is I will take this. I will put this right here. I guess this ELDM is my laptop machine. And let's, oh, I'm not sure. There's quite a lot of meetings. I don't know why we have this. Just curious on one thing. Let's go here. Miransha Kumarachi. Okay, so what if I do this? Dash RC again. Okay, so Elias, local service. Okay, let's put you again here. Miransha Kumarachi Atlas. Y minus. Your login name is the one that is. Who am I? Oh, that's you. That's me, I mean. Okay, so your login name is this. Let's source this and let's try it again. I'm just trying to automate my. It asks for password with funny thing. So what if I do this? Message. Copy this one also here. Okay, so will this work now? Oh no, I now understand what's happening. No, it's not because of this. What am I doing? It's actually my own. Okay. Okay, I now understand what's happening. I was asking why is this the case? Okay. No. Can I go here? So PWD, okay. Okay, so this is you. Yeah, I can't. Okay, I see now the problem. Okay, I can see it, but I can't do anything.
I can type password. Can I announce it?
But I can't, SSH. That's the thing. I have to, show you what's happening. Let me think. If you were here, I could ask you to type in your pass, but I don't want you. I want to know what your pass is.
I can announce it. Can I? I think.
You can do what?
I think I can type in your screen from here. I'm not sure.
No, you can't. You can't. Okay, so that's the thing. Yeah, I cannot change your files. So you didn't copy anything to Malatya?
Yeah, I have everything in Malatya.
But the simulations are running, so you don't have anything there. So
Oh, can you check? I run minimization step and heating step.
Just 1 second. No, I can't check it because I cannot do anything. Just give me 1 second. Thinking. I'm just thinking. Just give me a second. So if I do, okay, let's see. Let's go to my machine, and from here I go to Niransha Kumarachi Malat. Let's go to here. So you open a terminal and SSH to your Atlas account. Okay? I want you to do that.
Right now I'm on Windows.
But what are we gonna do? I don't understand. Oh my god.
I have those files on Malatya.
Yes, you are in Windows, but how do you SSH? How do you use Linux? You don't use Linux?
Right now I cannot because I have to go to Linux
Yeah, you should have it. Okay, so you should have PuTTY or something else. You need something. You don't need to just switch to Linux to do research. Okay, if that's the way you do it, that's fine. But you still have to have something at Windows. I mean, it can. I mean, I was using Cygwin, but then I decided to switch to Windows subsystem Linux because it's really useful. Some people are like, this, high school kid. He's using PuTTY to, SSH to the, servers. I mean, you have to use something. So what are we gonna do now? Can't do anything.
I have those files on Malatya.
Okay, give me 1 second. Give me 1 second. So I can be you in your. Okay, so I'm right now you in Malatya. Maybe I can. Okay, so let's see. I think I can. I understand. Well, no, you don't have anything. You always enter your password when you SSH to Atlas, right? Yes.
Yeah, I guess.
Yes. So you didn't even create the SSH files or anything. I see that that's not the case. Okay. So if I do SSH from your machine, Malatya, because I'm right now used to login.hpc fau.edu. Okay, why isn't it? What the hell? Oh, because of you. So it will ask for a password, and I don't know what your password is. I can't do anything. I cannot do anything right now. I am unable to do anything.
So the same files are located in Malatya. Can we check that?
But I also need to, look at your ND simulations. I don't know if because you already made a mistake. You already requested 3 GPU nodes.
Yeah, I'm going to stop that.
You requested 6 GPUs and you are using only 1. So I wanted to show you everything. Okay, so where is your stuff? Dynamic force field, is it here? Where is it?
Yeah. And
under test?
Yeah.
Okay, so what do we have? Which system? Is
and
it here?
benchmark? Yeah, and benchmarks.
Benchmark systems, okay. So you have one AL5. Is that what you are working on?
Yeah.
Okay.
No, 5 AL. Sorry, AL5 without 1.
Okay. One AL5.
No, AL5 without 1.
There is no AL5. Oh, what's the difference between AL5 and...
It is just a copy.
Okay. So, let's see. So you have... There's your xleap file. Where's your xleap file?
It is on benchmark system. Fold back. One fold back.
Okay, so I should, describe me what you are doing. I don't know what it's like, me trying to, understand what you are doing. Jesus. You already... Okay, I have to understand what you are doing. Okay, so what did you do?
I simply run minimization stuff.
Don't do minimization, nothing. Just tell me how you actually created the directories, how you created the PRM top files. What did you do?
Okay. I did NAM and then
describe the system. Like you have 4 systems. Which system did you start with?
I did with 1 AL5 and 1 NAM, one BNA and 1 SDR.
Okay.
Yeah.
Okay, so I'm right now 1 AL5. Okay, here what did you do?
Okay, first I created wait. Can you go one folder back?
You need to do this yourself. I don't like this. Install WSL. I don't like this. Install WSL. Next week we're gonna have you WSL. If you can't use next to WebEx, you have to be here, and you are not here, so you have to do something so that we can interact.
Yeah, I created those folders and using this SQUSH file. This is automatically create those folders and the PDFs.
triplet 1, declare blah, 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 blah.
First, I define the
I don't think
RMS.
that's the way it does that because I don't see these directories. So suppose that the sequence.sh is going to
Oh yeah,
create a.
yeah. I rename those directories later.
Okay, then.
Then go to 1AL file, for example.
Okay.
Then I source the.
By the way, I have to tell you one thing.
Mhm.
So this AL file which I downloaded, it's available in database in the PDB database. So that's the reason why I asked you to actually study these systems. You can, of course, design it using NAP, but there's already a structure there, so you could have used that one. Okay, so you use NAP to create the structures, and I checked it, and you renamed the names. I don't know how you did it, but you write a script to do that. And then after I created the correct file. So this is the correct version, okay?
Okay. Yeah.
So how did you create?
I
So what did you do then?
I create the PDB file and the 2.pdb file. You see that? And it was the correct PDB, my version.
Yes, yours was something. I think it was this one. So I created this correct one. If you do like a diff, you will see what the difference is. So if I do diff between yours and mine, you see that this terminal ones were wrong, so I renamed them. So 12 is the three prime end of the first strand.
Yeah, I did do that changes. It is on name like 2.pdb. Name is really changed. This third file.
2 PDB.
Yeah.
Yeah. Okay. So then basically, this should be exactly the same way as this 2 PDB. Yeah, I don't know. Yeah, it's like me trying to understand a maze. Let's see. Why are the sizes so different then? Oh, it's the. Yeah, but 2 PDB is not right. 2 PDB is totally wrong. Do you know why it is wrong?
Spaces between column.
Because what did you do? You can't use 2. Did you try to create PRM top file using the 2.pdb file?
Yeah.
It should have failed. It cannot create anything.
It, as I remember, it work. No, I can't. I don't remember that it worked or not. So
It cannot work.
So
the
later.
problem.
Okay.
The problem is that your the format of your PDB is wrong. Like you see, it's totally wrong. Like you have the atom, which the first 6. Okay, so let's see.
I noticed that one. Yeah, I noticed that one.
Okay, so it cannot work. This will not even work. Okay, so you have to be careful that you have to look at what the format of the PDB is. Okay. Okay, so what then? What did you do then?
Then I use your corrected PDB and create the INCPRD file and param-top. Then I ran the simulation.
Where is your xlib file? How did you create the structures?
Xlib file on one folder back.
Okay, so you use this file here?
Yeah.
Xlib
Yeah.
folder?
Yes.
Okay. Can you remind me why we are using this libRCRNA FF99? Is there a reason? Why don't we use like the libRCRNA FF9? Was there a reason? There must be a reason. I don't remember. Okay, so then you do this, you load. Okay, so attachment.
It is easy to manipulate the
Just give me
force
one second.
field.
Okay, so this is the. Okay, so this is the force field file, the library file. Right. See, right, and this is okay. This is with the alpha gamma revision.
Yeah.
Okay. Okay, so then you have the correct one. Okay, here's the thing. So you have to explain me because I don't understand it otherwise. So you have two, and you have the correct PDB. I don't know how did you create the correct PDB, or did you use the correct structure that I gave you? How did you do it?
I think later I try to create a PDF file like you did, but I can't remember what's the name. Maybe it is correct PDB or a.pdb.
I don't understand what you just said. How did you create the correct PDB?
I just use awk command on terminal and
What? You did what?
some commands on the terminal and
Okay,
just
you used awk.
yeah awk and just
Okay.
arrange this PDB file with correct spaces.
How
That's
did you do it? What's the command that you used?
I use a command. Let me show you.
Okay, so it's correct. So this correct.pdb is correct because it is exactly the same as mine. Okay. Did you just copy my correct file? Maybe that's the thing that you did. I don't know what you have done.
No. I just try to do like use PDB because I remember you show before there is a code to get exact structure of PDB file. So it is
Format, not structure.
yeah format.
Is it this one? So this is like so there's this file that I created, I think, called komutlar.
I got that
No, that's not
part
you did.
from the create
Oh,
from.
I see. I see. Okay, here's the thing. You have to write also a README file. The README file
Okay.
is important so that I understand or you remember what you have done. Like when you create something, always create a file and say, hey, I've done this, I've done that. I use this command, I use that, blah, blah. I see now what you have done. So you probably have that, catenate structure, and there's this printf command within awk, which was actually formatting in the proper way. Okay. So you have the correct structure, fine. And then you use the, let's see. So then you use the xlib file, okay, to create it. And within the xlib file, what you do is you initially source the librcff, that's fine. And then you source the water, which is also fine. We define all the new atom types. Then you specify the new, just like, rename all the atom names, which might not, which different, okay. So then this is the library file for the new RNA dimeric residue. And this one here is the FRC mode file. This is the correct FRC mode file.
Yeah.
But your namings are very different. Like, so you have dimeric force field, and then this library file is under test. I guess at the end, once we verify it, we are going to put them in a library. I don't know.
No, I just copy because I don't want to damage that file in case. Yeah, that's why I just copied it.
No, I mean, like, we could, do the following. So here, this is your, okay, maybe it's not actually a good idea. Yeah, probably. Okay, well, maybe is it? I don't know. Where is my stuff? So here we have the, okay, library RNA FF chi alpha gamma IY. So I put everything here. So you are actually copying these files to
Yeah.
test. So I don't know if that's, it's better not to do it. Just like, load these files rather than, copying it. You see my point?
Yeah.
So the files are already here. Don't copy it to test, because then it will be confusing. Do you understand or not?
Yeah, I do.
Okay. So, okay, let me think. So it's like this. So you have the FRC mode file here. So,
Yeah, same.
so it probably is the same, but you can double check it with this stuff. Yes, it is the same. Okay. Another thing is that, so this is explicit solvent, so it's not going to be affected, but the procedure should be the following way. So you create the PRM top file. Once you create the PRM top file, then you need to run the script that we wrote, which says correct PRM top. Do you remember?
Yeah.
You need to normally run it, but because this is an explicit solvent, it shouldn't affect it at least at the end. But I perfectly want every PRM top file to look like the old way. You didn't understand what I said, okay? Let's see. What's this? This is test. There's a lot of benchmark tests. Okay, so here, if you go here, so I have the testing done. So within the testing, we have, a lot of files. So create new okay, so maybe, what is it?
So in the bottom line, the printf to that, this is where I got the correct PDB format.
Yeah, okay. So then here's something that we have written down, which says create correct PRM top.pl. Do you remember what this was doing?
Yeah, it is correcting O3,
radius.
Yeah, O3.
The radiuses. So this is, very crucial. But it is important for implicit solvent. Nevertheless, even if you create the explicit solvent PRM top file, you still need to run this so that things are, the same. So for instance, let me show. So if you go to here, AA, as a test case, and we have water here, the new definition. So I have this new definition and the old definition. If I do diff with the old definition, there will be differences. So I didn't even run it, but you see, these are different. And it's better to actually make the files look like the old way. Even it's not used, it's better. I don't know, for maybe some reason it might be used. I don't know. Maybe, yeah. Maybe in, yeah, it's better to actually run it. But right now, let's not worry about it. But that's going to be the procedure. You have to create a, procedure on how to create the files. So you need to first create the correct structure, which includes like the new residue names. Then you are going to run the tleap to create the PRM top file. And then once this is done, you need to correct the radiuses by running the script that I just told you. And then once everything is done, you have the PRM top file. That PRM top file is going to be the correct one. Okay, so let's go back to your stuff. And in fact, I wouldn't even put everything to test because right now I don't know where they are. Too much directories.
Benchmark system.
Okay, so we go ALF. Okay. Okay, so we have it. So you actually created the PRM top new?
Yeah, I used that script.
Okay, so in your simulations, are you using PRM top.new?
Yeah.
Okay. So if I do PRM top, difference of this one, what are the differences? So it's the, let's see. Okay, I think it is this, yeah. That's different. So it should be like, 1 point, which one is this? Let's see. Why is it 1.5? Oh, because it is oxygen? Yeah, probably that's the reason. Yeah, it is either 1.7 or 1.5. I'm just curious on one thing, so let me do another thing. Yeah, it's the radii. Yeah, the radii needs to be corrected. Another thing which I forgot to tell you actually, what we should do again. This is not important right now. Okay.
Mm-hmm.
Just give me 1 second. Maybe it might be important. This is again all about implicit solvent, nothing else.
Oh.
I think the speaking shouldn't affect the explicit solvent. So here, how do I create the implicit? So I set the default Bondi as this. Did you set it that way? Okay, I'm lost. Okay. Let's see. Okay, so here. So you have to put right here this set default PBI radii to M Bondi, okay? So you load this and then you add ions. You don't add any extra ions, which is okay for this purpose. It's okay. Solvate model with this one, and okay. So then you create the model PRM top file. Okay. Once this is created, then you create the PRM top file. Yeah, it's okay. It's okay. So once this is done, once you have the PRM top new, then you created this directory called AL5.
Yeah, can you go to inside and I ran a minimization on that machine?
So another thing, before we go to minimization, we have to look at it. So this is your output file. Let me see. Oh, wait a sec. No.
Min.out.
On AL5. Because did you create the PRM top file here or in the next one?
The same directory, both are same.
But your TLEAP file is old. You don't have the new one. Where is the new one? This is not correct. You didn't run the you didn't. Okay, do you understand my point?
Yeah.
You didn't run the xleap file, so you have this xleap file. You didn't run this. If you have, or maybe. Oh no! You might have done it. You have so different names. You have tleap.output, and then you have the leap.log file. Okay, so let's look at the leap.log file. So probably you haven't done it here. So started, so it's probably the last one. Log started. So next, second one. Okay, so this is the last one. So this is done on June 11, 9:51. So let's double check. So you are loading the source file. Okay, that's what it does. And then you are loading the libraries. This is again the old library set. This is like, what the source does. It loads all the predefined residues and everything. And then you load the water molecule. I remember, yes. So here's so this is what it does when you source the tip3p water. So this part is for that purpose. And then right here, this is the part where you define the new atom types. Atom types are defined. We are substituting these atom names, which is fine. Then the library file is loaded. Read files. Then we are loading the FRC mode file. Yes, everything looks like properly. But then you are loading the correct.pdb file. And there are 66 atoms, which it finds that it is correct. Then we have add ions, so you basically add 22 ions, which is fine because you have 12 base pairs, meaning 11 plus 11 phosphate group, 22 phosphate group. That means you need 22 sodium ions to neutralize the system. Okay, so it adds those. Then you are solvating the water right here, this part here. So I'm also describing, what this tlib file does. This is lib.output file is. This is very important because if there's an error message, it's going to display here, and that can also help us, determine if there's any problem. But then there are warnings, which is fine. It will always happen. Okay, seems to be okay. So this is the first step. Once this is done, then you run this correct PRMTop file and create the PRMTop.new, right? So here we are going to do first. So there is a program called Parmat. It's part of Ember. Did you use this before?
In tutorial, yes, I don't
Yeah, maybe you have seen it in tutorial. It's very useful. So if you type in the PRMTop file that you will check. So if you type help, it's going to display what kind of commands it has. The reason why I'm doing this is that, remember what we have done is this. We are trying to use the naive chi definitions plus alpha gamma definitions for these naive residue names that we have created, right? So what I'm going to do is I will just check out what those numbers are for specific ones. So if you type in help, it's going to display all the commands that you can use in this program. And for my purpose, I'm interested in this print dihedrals. So if I write print dihedrals, I select, so I know that there are 24 residues. I will select the second one. Then I will look at what the torsions are near C5 prime. So automatically I see that there are like there is a torsion with periodicity 4. The way I create my torsions are always having periodicity 4. I know that alpha gamma for the PAN BSC force field, it has 2. So this one is, for instance, this O3 prime, P05 prime, C5 prime. So this is the alpha. I see another periodicity 4 torsion, which is O5 prime, C5 prime, C4 prime, CT prime. So this is the gamma, I see, because this is the definition of gamma. It's the O5 prime, C5 prime, C4 prime, CT prime. Okay, so this is the first step. And I also have a lot of, so you see this capital QG or lower GC. These are all new atom types, which has never been used previously. So I think that it seems to be okay. You can also check out, again, print dihedrals for the torsions, let's say. So I don't know what your second residue is. Maybe there's a way to actually display it. Maybe if you type in print details, star, yeah, it actually displays everything. This is too much. Yeah, I mean, this is a pretty, useful program. So I will, do print dihedrals. I don't know what your second residue is, but I'm gonna say N9. And yes, it seems to be it's purine. I don't know what it is, but this is the 4 periodicity 4 for the chi torsion, C8 and 9, C1 prime, C2 prime. There should be also the other version, the other term that is also required. So this is the O4 prime, C1 prime, and 9, C8. So these two torsions are actually defined the chi torsion. That's what I'm trying to. And it looks correct, I guess. It looks okay. I mean, I was trying to verify that this is indeed for a periodicity 4. If you are really anal about it, what you need to do is find out what residue this is, and then directly compare these numbers to the FRC mode file. That's another way you can do it. Okay, so we quit it. So it seems that your PRMTop.new file is correct. Seems to be correct. So if we go one directory up and then to the AR5 where we have done the minimization everything, right?
Yeah.
So what do we have? So we have the PRMTop.new here. And so, okay, what did you do? You did first minimization, and then healing. How did you do it? You have the file, the input files.
Yes.
Do you have that?
Yeah. One folder back, please.
Yeah.
Here, mdin min.in and heat.in.
Okay, so it's all our input. Okay, so let's look at what these are. The first minimization, then heating, and then MD. Okay, so minimization is, so you do like a simple minimization. I guess, this is fine, but next time what we are, oh, no, this is actually not right. Is it? No, it's actually okay. It's okay, it's okay. Maximum cycles 2,000, 1,000, 1,000 each, two different methods. And the cutoff is 8. Okay, I think it's okay. And then we have the heating. I don't know if this is correct. I mean, all these terms represent something. So this is the constant volume dynamics. So no pressure, nothing. It's just going to, heat the system. It's not the best heating method. I can tell you that. And also for each of, it will be better if you don't just like, each line, combine everything. So NTX5, this is the iris. You restart, it should be 1. Yeah. Overheating, it is 0. That's correct. So that's like a 1 nanosecond MD with time step 2 picosecond. So initial temperature is 300 NTPR. So this is how often you want to write. Cutoff is 8. So this is constant pressure dynamics. So pressure is 1 atm. It seems to be okay. In general, it looks okay, but we have to follow exactly the same way we did. I did before. So I will just show you something. So let's look at my publication. So where was this? So it was, where was it? Right here. So I think I put like input files maybe to the SI. I don't remember it, but that's, oh no.
I didn't notice that.
Where's the supporting information? Oh, it's P. Okay, let's see. Maybe I have it. I thought I did. I put everything there. Do I have any tables? Atom name, sample, Amber input files. Okay, page number 12. Okay, so you see, this is how I did it. So my way is different. So I have 2 steps of minimization. In the first step, I actually restrain all the heavy atoms and relax the rest of it, which includes water, ions, and the hydrogen atoms. In the second step, I am minimizing the whole system. And once this is done, I do equilibration. In the equilibration, I have again 2 steps of equilibration. In the first one, again, I'm keeping the position of the heavy atoms intact, like I use position restraints, so that the heavy atoms of the RNA doesn't change, but the rest is going to be affected from this heating. In the second step, I do the same thing again. I still keep the RNA fixed, it seems to be. When I say RNA fixed, it's the heavy atoms of the RNA. But now, the initial one is the constant volume dynamics. The second one is constant pressure dynamics. In the production run, it's constant pressure dynamics. And, all these data is almost the same as what you have. So the initial temperature is 300, final temperature, I guess, I don't know which one is what. This is initial maybe, that's fine. I thought this is initial. So, and this is the final one. The cutoff is 8. We turn on the shake algorithm. NTX iRest font means that this is a, what is it called? Restart simulation, 5. And iRest means it's a restart simulation. NTX equal to 5 means also take the velocity from the coordinate file. That's what it means. So if you have the velocities, that means that you also know what the temperature is. And then the cutoff is 8. This is constant pressure dynamics. I think this NTC equal to 2 and NTF equal to 2 means shake algorithm maybe. So IGB is equal to 0 meaning this is not implicit solvent. NTR equal to 0 means it's nothing is restrained. So if you look at here, here it is NTR equal to 1. Reason is that I'm imposing positional restraints as defined here. But in the production run, there is no such thing. So we set also NTR as equal to 0. And then this is my simulation time. It's 10 million steps. and the time step for each of the step is 2 picoseconds. So when this is run, it is a 20 nanosecond MD, that particular simulation. NMR opt means that there is no NMR optimization. So it's basically like geometric restraints that you can also impose, like distance restraints, proportional restraints. We don't do that one because we are not interested. And NTT equal to 3 means this is a Langevin dynamics. Gamma ln, I think, means, I don't want to say it wrong. What is gamma ln? I can't remember. This IG equal to -1 means that the random seed number is randomized. So it's going to be a number that the current time when you start the run is going to be a random seed number. This is NTP equal to 1 means this is a constant pressure dynamics. Tau 2 means this is the relaxation time for the pressure. Pressure 0 means what's the pressure, which is 1 atm. And I out Fm equal to 1 means write everything in net CDF format. So this is what it is. So it's something like this is my general procedure. That's what I'm trying to highlight. So you can use these type of input files in your simulations also as a reference. Okay, so let's look at here. I think everything looks fine. So okay, if this is the case, so let's look at what you have output files here. Let's see what those are. I think you ran these in your Malakia machine, right?
Yeah.
Okay. If you look at 0, 1, okay, first of all, you need to have a script. So for the minimization, I don't know how you did it. You seem to have done it in one line. Generally, write a full script. Okay, so I don't know what you have done. I'm just guessing. So, okay, it didn't actually work. What is happening? Okay, your minimization is not right. Where is your minimization? Oh, you have the min.output file. Yeah, you have, okay, look, you have to clean also. Like, what is this? 01 underscore min.output file.
Oh, it is a mistake. Sorry.
Okay, so you clean it. Okay, so this is the minimization. It runs this minimization file from the one directory up. Input CRD and your P on top new is being used. That's good. So when I look at it, it looks okay. Yeah, it looks fine. So then you have the heating. We call it heat.output, I guess. Yes. So increase the temperature slowly. Yes. At the end, it will be 300. Close. Okay, this is not finished.
Yeah, probably I might close the terminal.
You shouldn't have done it. Why then? MD output depends on that one.
Yeah, because I put it on the HPC.
Okay, MD output is also wrong. I don't know what you have done. These are not right. This is not like. Why did you close it? I don't understand. You could have done it like very easily. These are very fast calculations, even here. And okay, let me double check one thing again. How do you do it? So you are using sender. Why are you using sender?
Because we have problem with PMD.
No, there is no problem. Who said there is problem? If you are not able to use CUDA, there is no need to do research. You can't do research without code. And you have to figure out why this was the case, and you couldn't, figure it out. And you have to contact, David Cage wrote you back, and you need to, test it if it's actually working or not. You need to understand what this whole thing is all about, okay? You need to benchmark it yourself. And he said that the double precision is the reason. I don't know if that's the reason. I don't think that's the reason. we tested it, it was different. So I don't know. The only thing what I can tell you is that you have to figure it out. I don't know. It's so when we run standard, it seems to be okay. And then when it is CUDA, it's not. It's different. But the funny thing is this. I don't remember what we have done before. What did we do with the CUDA testing?
We try to simulate same system for CUDA, CUDA MPI and SAND MPI, and we get different result at the.
So here's the question: did we do the following? So did we do any single point energy calculation? So the single point energy calculation had differences compared to standard. Am I correct? What was the difference? I think it was the difference in the.
But he says there is no significant difference, so maybe probably we can use CUDA.
Here's the thing: we have to verify that that's indeed the case. He's thinking that if we are using the same force field, that's the case. But we are right now switching from one force field to our force field. So we want to make sure that it is actually the case. You can't say that, but I would like to understand what this whole thing is all about. Let's go back again. Let's test it again. I want to test it. Because now we have the correct PR, kind of seems to be we have the correct one. If you go to testing, let's go to AAA. Okay, here I have gas, implicit, and water. Let's go to water. Okay, so we have the old definition, we have the new definition. And I'm using standard here, right? Maybe go to old definition. So the old definition is assuming that it's correct, okay? So what I'm gonna, and we can even look at what this is. So we have used just like PMEMD or standard, yeah. So we are going to use the CUDA. I'm gonna create something called CUDA test, okay? And we'll go to CUDA test. And what I would like to do is this. We're going to use the same input CRD. And in fact, maybe what we should do is this. Not in this case. Like we are on CUDA test. So PMEMD, okay, so here we have the current PMEMD CUDA is this single precision version. There's also double precision version, which is this one, high. So what I'm going to do is this. Make directory SP, what is it called? SPFP, and then I will call another one DPFP. So we are going to create two different data, okay? The SP, let's go to the first one. And what we are going to do is we are going to run specifically this one. Where's my, so, and then let's write the whole thing, okay? Overwrite it. My PR top file is this file. My coordinate file is input, what is it called? Yeah, input CRD file. What was my input file? Minimum.in. What file are we using? Min. Is it min maybe? Yeah, probably it is that. And then my output will be min.output. Should we minimize it? Let's minimize it, okay? Let's minimize it. and the restart file will be called min.ist. Let's run it at the background. It failed. Why? MEMD. Okay, so this is my input file. Why did it fail? I think we made a mistake. So, oh, it's right here. I didn't specify what that file is. It's input file. So let's run. Okay, so it's running, right? It's running, right? So let's look at what this file does. Okay, so it's like, 150, blah, 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 all sorts of numbers, right? Okay, so this command does work, right? So here's what I'm going to do. Actually, I'm going to remove again everything, and I'm going to do this following. So let me copy this full line, and I'm going to run it 10 times. Okay? Let me see. Print. Line. Let's see if this is cool. Oh, didn't. Oh, I have to use a for loop. I'm sorry. For $i equal to 0, $i less than or equal to 9, $i plus plus. And this is my. Okay, so we are going to run it 10 times. Oh, this is again not the best approach. Give me 1 second. So we have to create make directory $i, cd $i, and then run this one. Top file is this one. This is the input CRD file. Minimum file is that. Okay, write it down here. And once this is done, go in directory. Okay, so it's going to create 10 directories, and it's going to run the commands, the whole thing. Okay. I'll create all the things. Okay, so $line. Okay, so let's run it. Let's run it at the background. So it is, okay, so it is running. For instance, what happened? 0. Yeah, it seems to be running. Okay, so it's going to finish very fast. Let's give it a couple of seconds. Okay, so it's done. So what do we have? We have run 10 MD simulations, test simulations with min.output files, right? So I'm interested in what the differences are. So I will first, write a very short awk script where I'm going to store the files. Once this is done, I will do a loop for $i equal to 0, I equal to 1, I less than or equal to s, I plus plus. Maybe it's going to be s minus. Yes. For j equal to I plus 1, j less than or equal to s, j plus plus. My command will be diff of di and dj. Print k. Yes, it's going to be how many? 45. Okay, so let's do it. System K. Okay. So here's the thing. The energies and everything are all the same, okay? So there's no problem. The minimization is exactly following the same minimization. The energies and everything are the same, okay? So this is the first step. Now, what we're going to do is we are going to apply the same thing for the DPFP, okay? We do again the same thing, but now, rather than using the so here in this line here, it's going to be not SPFP, but it's going to be DPFP. Okay?
Okay. Yeah.
That's right. It will take more time. If I like try to figure out, I think it's really, yeah, it's very slow. But still, let's keep it running. So you should have done this before by yourself. Okay? How many steps did we ask? So it is 1,000 steps. Okay, it's not like, so crazy. So yeah, so it took like 30 seconds. I think it took like just 2 seconds in the single precision mode, right?
Yeah.
Okay, so I'm just curious on one thing. So if I do like a diff between min.output, this is with the bar, right? Okay, with the SPFP, let's say just like this one. And yes, there are like, differences in the energies, and that's what we were seeing, which is normal. That's what we have observed, okay? So the energy difference seems to be like not so high when you compare SP, the single precision, to the double precision. And I think at the end, that's what they generalize. At the end, it's still useful to use SPFP because like you are gaining quite some time. It takes 2 seconds in one case, the other one takes like 30 seconds, like it's really, slow. Nevertheless, we have to still, the whole reason why we are doing this whole benchmarking is because we want to make sure that the new way we are defining the force fields do not affect the predictions. So if my single precision data so okay, we will see it though. I will tell you what we are gonna do. So let's see. It's gonna take like what? 10 runs, 30 seconds, 5 minutes. And you will have only one GPU, so let's just keep it running. That's another thing. Like, maybe the results will be different when you are running this, same job, not in your machine, like which has this Quattro K620 GPU. If we have run it in, let's say, in the HPC cluster where we have the V100 or this P100s or this Titan X cards, maybe the results will be different. Do you see my point? It is possible. Like, this is a benchmark that you need to do. I cannot test everything, but this is just a way of telling you how this is being done. So once this is done, I'm gonna again look at the diffs between 0, 1, 2, 3, 4, 5, 6 to see if they are different or not. And let's see. Then once this is done, we are going to do the same thing with the Neve definition. Okay?
Mm-hmm.
So 7, 8, and 9 is missing. So let's look at the history. We are going to yeah, I'm gonna run this one once everything is ready. So let's see. Just less than 1 minute. Okay, so this is the last track. How long did it take? 29 seconds. Okay. Okay, so it is done. Let's look at the differences. Okay, now we have something very interesting. Yeah, why is this the case? So this is funny. You see, there is quite some differences. So we have run, 10 DPFP calculations, right? If I look at the outputs of the first one and the second one, which should be exactly the same, right?
Yes.
Right? They are not. We are seeing differences. Small, but there are differences. And so old definition, right? How did I create the old definition? X sleep. So this is explicit solvent, right? Yeah, this is with the water. X sleep old water. Okay, so let's do something else. I am right now a little bit pissed off right now. I'm actually very pissed off. Okay, here's what I'm going to do. Make directory CUDA testing. This okay, within the CUDA testing, I'm going to just like create something. Okay, you are going to see what that is. I don't know if this is about the new atom types that we have. I don't know why this is the case. Honestly, it's kind of really weird. If I look at AAA.pdb, let's look at what this file is. Okay. So this is like a regular RNA review, right? So I will copy this one to here. I will then copy the XLEAP file, water, to here. Okay. Now I'm going to call this XLEAP all to the XLEAP.info file. I will open this file, and here's what I'm going to do. I will say Alt-FF, leap RC this, fine. No new stuff. This is fine. I'm going to use the original wrong parameter set, okay? I want to see if that is actually the case. And then here, what was this called? AAA. And I will, solvate it the regular way. So we have elite minus xd. So this will create a PRM file, as you can see here. This is what people have been using before, without the chi or the alpha gamma revision. So for instance, just to highlight what I've shown. So if I look at the Parnax stuff, when I say print dihedrals of the second residue C5', you see there is no 4 periodicity result. This is the old force field, the wrong one, Amber 99 force field. So for instance, look at print dihedrals. And 9, so this is the chi. You see that my chi is not here. No chi is defined. So this is the old way, very old way, okay? This is fine. So I'm going to call SPFP, DPFP. I will go to DPFP because we saw this problem there. And history, what was the history? Okay, so maybe I should do the following. I go, do I have a file here somewhere? Is it here? There's anything where was it? Okay, what I'm gonna do is doesn't matter though. I will copy this one. So this is like a minimization. Maybe I should do the following. Move run min. Okay, this is a problem. So move run min. I will call it just run min.dpfp. And here I will say run min.dpfp. Okay, so let's see. We're going to call this PMEND. What was it called? So the name is dpfp. Let's just so this is my minimization. So it's 20,000 steps, which we do not want to do it. I'm going to do just 1,000. 1,000 even is too much. Maybe let's do it 500. Let's make this 50. And cut off. No, this is not right. It should be 8. And TB is equal to 1. Yeah. Oh, no, these are wrong. And oops. Okay. Oh, I see. So this is like doing single point stuff like. What did I do? Did I copy the? I should have copied this one probably. Let's copy this one. Let's rewrite it again. Okay, so this is better. So what was it called? The name is again DPFP. Okay, so this is my run. 1,000 steps is still too much, I think. Let's make it 500, as I said. This is 250. MTB, yeah, this is correct. Okay, so we are going to run again 10 times. Because now, do you understand what I'm trying to do?
Yeah, I'm trying.
Using the very old force field. No extra atom types, nothing. It's the old force field. And normally, if we run 10 DPFP calculations, it should actually give me the same result, which it does not. So this is the funny thing. I'm kind of, therefore, like a little bit, surprised. So here, another thing that I need to be important is this. Okay. And this is again. It says the yeah. This is not, which is not important, but yeah. So let's run it. Same stuff that I would like to do, but the name will be the following. So go here and run man called runman.dpfp. And okay, so it's going to do this. Make directory, cd to that directory, run it, and then go back to it. Let's see. Okay, so it is going to take 2.5 minutes approximately. Yeah, it's we have to do this. I need to understand what's happening. I don't like it if the DPFP is different than the single point, because here's the problem. David was saying that PMEMD or standard result should be similar as the PMEMD the double precision version, right? That's what he was saying.
Yeah.
Right? So the issue is that if I run DPFP 10 different times, they give me 10 different results. There is no way we have a single energy result. And I don't like it. Now, the question is that the following. Is it possible maybe the new atom types are somehow causing the PMEMD code to the CUDA version to mess up? So, what do? We create the PRM top and input CRD file the old way. So this is the very old way. So there is no new atom types, nothing. It's like the original atom types. So if these results are going to be different, then it is possible that there is the atom types might be somehow interfering with the PMEMD CUDA code. Does that make sense? That's the reason why I'm running this test case.
Yeah, I understand.
For some reason, it's very interesting. The single precision version actually has the same the results. So we run it 10 times. If I looked at the output files, 1,000 step, output files, they look the same. I would have expected the DPF be the same, but it's not. So that's what I don't like it. It's going to be done like maybe 30 seconds. So this is the last run. I have to review a paper by today. So after you, I'm going to work on that one. Okay, so it's done. So let's look at it. Let's first just like do diff 0 min dot output with the first one. They are different. You see? They're different. They are different. Yeah. So what does that mean? I guess like we are still, so we need to still, depend on CUDA. Why this is happening is a different issue. I think they need to somehow fix it. Whatever they have is causing the system to somehow calculate different energies. Even though the energy is really low, and it is going to be like, okay, it's still, small, but still I don't like it. Yeah. Well, if it was small, but now it's increased. Yeah, it's, yeah, I'm not sure.
Is there any way? Is there any way that we can observe like 100 joule difference or something?
What?
Is there any way that we can observe difference with like 100 kilojoule or something? Like it is here, it is like 0.0 something.
Yes. So what's your question?
So is there any possible way that we can observe a very big difference somehow, anyhow?
Well, this is minimization. So the question is that when you are like, how does minimization work? You can think of like an energy sphere at this point here, and it tries to, go down the line so that it finds the minimum. For some reason, there is a chance that when you run independently at one run, it will go to this point, another run, it will go to another point. And this is not an MD simulation. That's, what I don't like it. This is not MD simulation. It's just minimization. Minimization should actually put you to the same location at the end. So if it was like a MD, maybe the random seed number was going to, put the simulation structures, conformations to other locations. But here, I don't like this. This is not normal. And this is the funny thing. I think this is like a problem with the PMEMD CUDA by itself. Because it's not about force field. Because this is the old force field.
Yeah.
Still, so I don't think it's all data. Okay, so this is what we have verified, which is fine. So if I go to, now this was just a deep, I didn't do it for SPFP, there is no need for SPFP. Okay, so if I go back to my AAA system and the old definition. Okay, so that was one test. Okay, we have DPFP, we have SPFP. We know that DPFPs are different, SPFPs are the same. So what I want to do is this. Go to the new definition, and here I will create again a directory called make directory CUDA test. Go to the CUDA test, make directory SPFP, okay, go to SPFP. Now I'm going to run again 10 simulations, okay? And what those, I don't remember. History, graph, SPFP. Okay, what did we do? Okay, so I guess, so Perl, make directory, CD, is it this? Not sure you will see it. Let me see. We have the PRM top file. Okay, I didn't create the. Let's create it. Maybe I should actually create it. Yeah, the correct one. I mean. Okay, create correct PRM top. So now we have the PRM top dot new file. Okay, so if I do PRM, let's see. Yeah, it is those differences, which is fine. Yeah, that's what I was expecting. Okay, so let's go to CUDA test SPFP. So what are we going to do? We run a Perl script. In the Perl script, I create a directory. Then I'm running the SPFP file. So the PRM top new is going to be used. Input file is this, created, and then, yeah. So let's run. So this should be very fast. Each is like 2 seconds. So we have 10 rounds, 20 seconds. Within 30 seconds, it should be done. And then we are going to look at what the outputs are. Okay, so history, corrective. What was it? Okay, so we use this differences. ls this, diff, okay. Okay, so yes, everything seems to be fine for the first comparison. You see my point?
Yeah.
So there's energy difference. These are like, how long it took to, this, I don't know what this non-bonded, this is probably related to times, nothing else. I will check it out though. So, non-bonded, okay, so this is the last part. Okay, so Joe 8 actually. I'm in the output. I'll search for this. What is this? Yeah, it is the time required. So the non-bonded interactions are actually the time-consuming steps. Okay. Okay. This is fine, right? So here's another thing that we need to do. Okay. So what did we verify? We did single-point energy calculation, and all of the single-point energy calculation actually predicted the same files, same minimization, let's say. But this is for the new one. Is this new one different than the old one? That's another thing that we need to do. If I do diff 0 as a reference, because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, they have exactly the same min.output file, okay? And I just use it as my reference one. Then compare this one to the old new definition, old definition, old definition, CUDA-test, SPFP, 0, min.output. Let's see if this is different. Again, the only difference that I see is the timing. So what does that mean? It means that whatever we do with the old way is exactly the same as ours, the current one. So this is a good test, okay?
Yeah.
Another thing that we forgot to do actually is the following. So let's go back to old definition, because we already ran the DPFP, right? So I'm just curious on one thing, DPFP 0 min.output, and I will compare it to my standard calc, PMEMD calculus. So this one at the bottom is like this correct values, and this is DPFP values. This is what, what's his name? David Case was suggesting. Maybe, that's the same, which I know it's wrong, but I'm just curious on checking it out. So, yeah, so this part is totally different. Yeah, that is totally different, electrostatic. I think what's happening is the following, honestly, if you ask me. This is water simulation, right? We have explicit waters. I think there is explicit water here, right?
Mm-hmm.
The explicit water. I think the cutoff that we use have different values. I think that's the main reason. So in one case, we have this DPFP. In the other case, we use the PMEMD. I think the cutoff that is being used for the boxes are different. Even though I specified to be like 8, even like slight difference will be creating issue. So if I look at diff, I think that's the reason. So if there is any difference, it should be at the beginning. So there is random seed number. Is that even possible? That might be the case. Which might be the case. Okay, so how did I run this DPFP? I don't remember it. Or maybe it is the what is it? Is it possible that this is the reason? Okay, I'm gonna copy this one and put it here. And I will say min. Okay, I will set IG to be equal to 666, just like one number. Or if I do this, okay, I will do. It's like a lot of checks that we need to do. Okay.
Yeah.
It's very hard to determine where the problem is. And also look at this one. Oh, the IG numbers are different, but it shouldn't affect. This is minimization, so it shouldn't use that. Yeah, I don't know. If I look here, so it uses a different random seed number. So note, random seed to evolve clock time in microsecond. But this shouldn't affect at all. And random is equal to 1. Okay, so just to double check on if this is really the case. Okay, so I'm going to go back to 0. Maybe, yeah, let's go. I'm here. So I'm going to, I'm just going to run this. Because now the random seed number is specific. Okay? Let's keep it running. And then I will do the same thing with the first one. Come on, come on. But I think it's I think the main reason is the box information. Maybe a slight difference actually affects the results. So we are setting the cutoff to be 8, but what if it is like 8.0001 something? Because if it is electrostatic, the energy difference is electrostatic. It might be bad because the bonds are the same, torsions are the same, everything is the same. Van der Waals is the same. Maybe that we are lucky. Maybe Van der Waals and the electrostatics are actually different. But yeah, I think there is a bug in the CUDA code, if you ask me. Okay.
Okay.
And I might even send an email to the mailing list. No, it's still the same. So we have two different, we have the same random seed number, but they again produce different. Okay, here's another, look, there's a lot of things that you can actually come up with, okay? So the error started at 550. You know what this means? The difference started to happen at 550. You know what this means?
No, I don't.
So remember, our minimization is 1,000 steps, right?
Okay. Okay. Yeah.
And we specified the first 500 to be, I don't know what it was called. I think it was called steepest descent minimization.
Mm-hmm.
500 is conjugate gradient minimization.
Okay.
So the first 500 doesn't have any kind of a problem. The difference starts happening in the second part of the minimization. Do you understand what I'm saying? If not, tell me. So there are two different algorithms in Ember. Steepest descent and the conjugate gradient. Steepest descent minimization is that if you are far away from the minimum, it will in a fast way, it's going to bring down close to the minimum, but it's not going to be near the minimum because it's a fast way of coming. But then when you do the conjugate gradient, it's going to slowly try to put you back, bring you to the global minimum. It is possible that that might be the case. So would you like to test it? Yes, let's test it if that's indeed the case. So how can we do it? In the input file, you see that we have 1,000 maximum cycle, and cycle 500 basically means the first 500 are the steepest descent. So what if I say 999? It means that first 999 steps are the steepest descent, and the conjugate gradient is just one step. Okay, so that's what we are going to do. And I actually would like to write the data. What was it that we were using? At each step, I would like to write the data. Which command did we use for that? We used something. I don't remember. Is it here? No. Maybe it's on the test. All downwards, right? We did something before. No, it's not this. Okay, I will figure it out. Just give me 1 second. I think. So let's see. Oh, it's actually somewhere here. I think it's NTPR. So let's say, in fact, what we can do is we can actually use all of them. Doesn't matter. I'm going to say this, but I will change everything to 1. At each step, to write down the output and everything. Okay, that's what I want. So that we can actually pinpoint where exactly the problems happen, right?
Yeah.
So this is another test we are testing. So this is what you should do, okay? All these type of calculations that we are doing is basically that. Okay, let's run it at the back. Let's see. It's going to take a little bit more longer because we are writing at each step, you see, down everything. 257, 258. So all those information is written. But it's going to be still fast. It's just 1,000 steps. So let's go to 1 and do the same thing. You see, actually it took 28 seconds, so time-wise, it is the same then. That's fine. So once this is done, we are going to diff 0 into 1 outputs, right? And my hypothesis is that the first 999 step is going to be the same. Only the last one is going to be different. This is the hypothesis. So that actually will help us pinpoint a little bit more. Maybe, the conjugate gradient method is actually the one that is causing the issues. So, okay, we are done. Let's do diff 0 min.output with 1 min.output. Here's the funny thing. They actually predicted the same stuff. How is that possible? Huh? Tell me. Huh?
So
this is funny. I don't like this shit. Oh my god, this is horrible. Okay, so here's another thing that I would like to do. This is really funny. I mean, when I say funny, that's actually depressing. Don't get me wrong, it's just depressing. Okay, so this is the old definition, right? Okay, so 4. Okay, so we did already 1 and 2, 0 and 1. Let's start from 2 to 9, okay? Make directory this, blah, 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 blah. The PM top. Okay, the input file that I would like to use is not this one, but the one. Okay, so now this is supposed to, let's see what will happen, okay? Maybe in this way, it's going to actually give me the same results. So what will that imply then?
Continue query methods.
No, wait a sec. I'm actually still correct. So what will we actually compare? The hypothesis was that the first 999 will be the same, right?
Yeah.
And only the last step will be different. Maybe by chance the last step didn't affect that much, and that's the reason why we actually saw that no big difference. I think I'm still correct. I think it's the conjugate gradient that is actually the issue. I think what will happen is that all these results that is going to be spit out is going to be the same. So for instance, the second one is done, right? Okay, so let's compare 0 min output with the 2 min output. Yes, it is the same. Let's do it with the 3. 3 is also done. It's the same. You see? Reason is that. So the last step. Let's go to the last step. This is the 0th run. This is the 3rd run. And I think what happened is that up to here, everything was fine, but the last one didn't affect that much. Maybe that's the reason why we are seeing exact same result. But if we separate it to first 500 and next 500, maybe maybe we should have done it a little bit more. Rather than 999 to 1, we should have done it 995 to 50 or something. So that the first 99. You see my point though.
Yeah.
Yeah. Okay, so if I do this, yeah, it's the same. So I think that's the. Okay, so this is something that I probably need to contact them because this is like a little technical specific.
Yeah.
Do you have a problem with your connection?
Yeah, I think.
Not this one. Amber manual. I will show you what exactly I mean. So the command that we are using is called maxcycle. So the last part is like the keywords. You can find where it is. Maxcycle. So 1.1336. I think it's somewhere here. Yes. So max cycle, the maximum number of cycles of minimization. End cycle, if nt-min is 1, then the method of minimization will be switched from steepest descent to conjugate gradient. Okay, so what do we have? My end CYC is 999, right? So it says that if nt-min is 1, then the method of minimization will be switched from steepest descent to conjugate gradient. So if it is 999, it basically says that after 999, it will be conjugate gradient.
Yeah, I understand.
Let me see. I think there is somebody has to test it. It might be that the dx0, the initial step length, is the cup, or maybe this is the convergence criteria. Maybe DPFP has a different convergence criteria. So default is 10 to the power minus 4 kcal per mole. But I don't think that's the case. I think it's something else. So yeah, I think it's the conjugate gradient that is actually causing it. But at least we figured it out. We figured out where the problem might be. I think we are done. So if I do like 0 min dot output to 9 and the output, it's the same. There is no difference. So it seems that the steeper descent minimization is kind of working fine. Now the question is this. We still see differences between single point energy calculation to the, I mean, somebody has to study all the properties and then summarize it. I can't try everything right now, but at least we kind of have this idea. We kind of have something. Yeah. Okay. Anyway, so let's go back to your original system. Okay, we are gonna stop in 20 minutes. It's going to take like it will be always like almost like 2 hours. Okay, I have to do other stuff. But you understand what I'm doing, right?
Yeah.
You have to do it yourself if you need to. So let's go to. So where was this benchmark systems, right?
Yeah.
So we were looking at AL5, right? So you didn't run it properly, but your files are running at the HPC cluster. Okay, so let's go back to the HPC cluster. Okay, so SQ, come on, rep and Iransha, come on, okay, so S control, show job. So this is like Slurm commands. S control is Slurm command. This is going to give me all the details. So if I look at what you have here, for sure you have made a mistake. Definitely made a mistake. Okay, so here, what did you do? Which script are you using to run the command? To tell me, because it's I see that it's the run.sh file.
Yeah.
What do we have? Okay, so you say n is 32. Okay. Well, first of all, I have to tell you one thing. You don't use the GPU actually. You are using the CPU. And the funny thing is that you ask for 32 CPUs, but you use just the serial version. You don't even use the MPI. This is not right. Okay, so then what else do we do? What do I see? I see that you are, so heat.ncrst is all are wrong. Because you didn't minimize it properly. You didn't heat it properly. You're using the file which is not good. So I suggest that you kill this job. This is not correct. And then send an email to Amir and Kai and ask for a sample Slurm script to utilize CUDA, okay? Yes, that's what you need to do. And here in your account, let's go to your account. This is your account, and this is AL5, right? So and also, what the better way will be is the following. It's better to write a script that does everything. So how did you run everything? Do you remember?
It is a single line code. I didn't use code for the simulation. Any script for the simulation.
So you have this right? Okay, so what I'm gonna do is this catenate this. Actually, this is not good. Catenate. First, it will be minimization. Then e. Then md.in, and put it in a file. Let's call it run min eq. Actually, I'm not sure why you need the md.input MD.input shouldn't be put here. My suggestion is that minimization and heating should be done in your local machine, which is Malatya, but the products, which basically means MD runs, should be done in the HPC cluster. Okay, I'm going to call this SH. So I'm going to, so what do we have? In this directory here, and also I will change 755. What is it called? Run min blah, blah, blah. Okay, so I have the run min EQ stuff. So here, what we are going to do is we are going to rewrite everything. And honestly, I think it will be good if we have my way defined. Actually, it will take some time to okay, so MSH, and maybe I should, always use my sample scripts. So here I even have like this run min stuff. Can even copy this. So what do we have here? We define it. So I will set the sender. Okay. So what I'm gonna do is this. We're gonna, oops, no. Oh shit, I did it wrong. No, actually, no, I didn't do it. I'm sorry. No, let's do it this way. So we can use bash shell. Okay, maybe. Okay, let's use C shell because the commands are different. So that's that. So here we are gonna use what? pmemd.cuda. Okay. And then we don't need to remove it, or should we remove it? Okay, so we can say bin /bin remove minus min.heat, let's call it this way. And then we are catenating to min.input file what? This. Minimize. And then here we are going to do end of file. Then we do the same thing for catenate heat.input. Actually, maybe we should call it here. Min.input here. Heat.input. Maybe I can do the following. Minimization. Heating. Let's do it proper way, okay? Then end of file. This heating stuff. But I will change it, okay? I don't like your heating results. Is this correct?
I got it from the tutorial.
From what?
Tutorial page. I refer.
Tutorial they have? Okay. Okay, so I'm gonna do it my way, okay? But here you will get confused, but you have to learn it, okay? One of the things is this. So I'm going to follow exactly the same way I do it. Okay.
Yeah. The question is how we follow the RNA fixed part.
Fixed, right? So the thing is that you need to know which atoms you wanna use position and restraints. And what I'm gonna do is the following. I will first create the correct way of the system. It's new, right? C and input PRD. I'm just creating a PDB file. I call it AATM. The namings are correct. Okay, so in this file here, I'm going to grab atom, but I do not want any water minus E. I don't want water, and I do not want sodium ions. So when right? So all the RNA residue atoms are specified here. But what I would like to also do is this: grab minus V hydrogens. I do not want hydrogen, and hydrogens are defined as space H. So if I do it, all the heavy atoms are displayed here. So then the next step is this: I will say print. So the format is atom and the atom name atom. print atom. Atom ID is $2 and $2. Okay, so this is correct, and I will direct this to a just temporary file called tmp1. Then I also would like to do the following. I will copy run min. I'm going to call it run eq.sh, and I will rename the run min because it will be too much to actually do both minimization and equilibration in the same file. I'm going to separate them, okay?
Mm-hmm.
Now I have run min and run eq, and I will put now all those TMP stuff to here. How do we do it? So how many steps do we want to have? I will just copy paste my stuff. Okay. You should actually combine it like this. So and over here, what do we have? We have hold RNA fixed. Hold RNA fixed. That's it. And then we define the force constant. I set it to be 10. Let's make it 10. And I just copy pasted it. So it is copy pasted here. End of file. And here I would like to actually call it I call it min1. Okay, so here what I'm going to do is I will create min1 and min2 in this file. And the equilibrate, the heating part is going to be wrong. Look at second minimization. I will call it now min.in, min2, and again, second minimization. You can even go up here and say this is first minimization. And in the second minimization, I do not put any kind of a restraint. So it is all just regular minimization. Okay?
Yeah.
And TV is this, that, blah, blah, blah. We put this one right here. Oh, for the atom here, I forgot something. I have to put and. Yeah. Okay, so this is the second minimization. So let's see if this will work, okay? Oh, wait a sec. You didn't run anything. So how do we run it, right? So once this is done, run the minimization. Okay, so it will be, I specified my sender as PNEMD CUDA, so I'm going to call it $sender minus override minus input file is min.input file 1, and the PRM-top file is PRM-top.new, I guess, right?
Mm-hmm.
Coordinate file is input CRD, output file is min1 output, restart file is min1.rst, that's it. And reference file is input CRD file. And the second step will be the same thing, except now it's going to be min2.input file. This is correct, but here the coordinate file is now min1.rst. Output is min2. This is min2. And reference is this, but it's not going to be used. Okay. So if I run this, what happens? It is running. Maybe we should actually remove the that's the previous minimizations that we have done, and maybe even this one. If I type in, it is actually minimizing the system. Okay, this is being done. So let's also look at the equilibration stuff. In the equilibration, we are going to do 2 steps of equilibration. EQ1, EQ2, equilibration. First equilibration. In fact, let's do the following. Let's copy run min, run min to run equilibration. Run equilibration to EQ1, EQ2, first equilibration. Okay, so here now we have to specify a lot of things, and that's going to be this whole thing. Let's see. So I min 0, restart, I think it's correct. So we still use the hold RNA effect stuff. Okay?
Yeah.
This part is okay. Now the second equilibration. But this will take some time because this is serious, calculation. EQ2. Over here, we do the same thing. Now, should we do exactly the same we did it here? I'm not sure. Also, one thing is that the force constant is not 10 but 1. Let's change that one also. Yeah. Let's make this 1. So should we follow exactly the same way? Let's follow the same way. So I will just copy paste again this stuff here. Okay. Okay, so here then let's also restrain the system, because that's what we are doing. We will still, hold the RNA suffix. We'll copy paste this over here also. Okay, so we have, what do we have? We have 2 steps of equilibration. Yeah. And yeah, the equilibrations are 2 nanoseconds total, so it will take some time. Let's also change this min to equilibration. 1, 2, 3, 4, 5, 6. Okay, sender. Okay, EQ1, here on top new. Okay, here this will be min2.rst file. Output is EQ1. Okay, restart is this, and minus x EQ1.mdcrd. Reference is min2.rst. Okay, the same thing also here, ref min2.rst. But let's go back here. So this will be the coordinate is EQ1, yes. Output is this, that, yes, this is correct. And this minus x is now EQ2.mdcrd. Okay. Run the equilibration. Okay, it seems to be okay, but let's see. I think the minimization is done. Okay, I made a mistake. That's corrected. Is it maybe? No, it's actually correct. I made a mistake. Okay, so we are running everything in your local machine, okay?
Yeah.
This is minimization equilibration. The production run should be done in the HPC cluster. One of the other things that I would like to highlight is the following. So you are, doing everything in your directory, but it's not ordered. It's better to actually have like a prep files directory where you actually, prepare everything, and then, run the. So everything is like here, like PDBs and everything is in the same file.
Yeah.
I don't think this is a good thing, okay?
Yeah.
It's better to actually separate them so that it's easy to read it. So let's clean it a bit. Remove TLEAP, that is also not true. Yeah, okay. And okay, so let's run the equilibration. And I'm going to run this at the background. Okay, so that we are going to stop here at this point. But if you just look at it, you see that this EQ1 starts to write. So if we look at what kind of output is happening, okay, so we have it seems to be okay. Temperature is 0. That's what we were expecting because its minimization has been done before. So this restraint initially is 0, but it will be a positive number because it's going to try to keep those heavy atoms close to the initial position, but they will be basically fluctuating. So okay, once this is done, you see, yes, the restraints are getting positive. And yeah, it will take some time once it is done. What I want you to do is prepare the input file, again, by looking at this, production as an example. Create an input file that is going to look like mine, and then we are going to run it. And we are going to use CUDA in this case. Okay? So no sender or PMEMD. It should be PMEMD.CUDA. And how did you submit your job actually? Do you have a Slurm script? I don't know. Maybe it's here somewhere.
Dr. Kai told me how to submit jobs to HPC.
Yes, but where is it?
Wait. I think I wrote that one on the HPC.
Oh, I see. Yeah, I see. And also, make sure that your Windows subsystem has a terminal where we can actually pay. Because what we need to do is, I need to copy paste my SSH key to your home directory so that I can automatically SSH and play with your files in your HPC cluster. Right now, I couldn't do it. So make sure that you have a running terminal in your Windows system, okay? So let's stop here and check out this file that is being created. If you look at here, it's basically it. In fact, what you can do is even run the production runs here if you want. Honestly, you can still run because you have one GPU, you are not coming here, so you can still use one GPU here also. That might be actually okay. So try to maybe run it here. Okay. If we go back to the paper, let's go back to the paper. So this is the one AL5 system, right?
Yeah. This is.
Let me see. This is the methods part. You should, look at the methods part. Post filtering, blah blah blah. Preparation of the system. So this is the single strand, and also we did it for one AL5. So even though your solvated water numbers will be different, and the methods are going to be a little bit different, let's keep it this way. The simulation time. I don't know.
I said 2. Yeah.
One ALK. This is one ALK. What's this? 2 POC. One AL5. Oh, I called one ALK. What is one ALK? Is this a typo?
No, it is not a typo. It was defined in the paper.
Oh, I have one ALK. So why are you No, it's one AL. This is one AL5, not one ALK. There is no one ALK, is it? It's a typo. Let's see. One STR and one BNA. One STR, one. Yes, this is a this is a typo. Yeah, I'm not sure if there's even structure called one ALK. RCSP. Go back here.
The structure is defined on the paper, so I prefer that one.
No, you don't understand what I'm saying. So 1ALK is a protein. But I made a typo here. So this should be 1AL5. Okay, so A is that. So it seems that I've run it for 1 microsecond. So you need to run 1 microsecond. Okay? I want you to run 1 microsecond. So this is that. Okay. Okay, so right here, I don't know how long it takes. Let's create also the input file for the production run, okay? So I'm going to call it md.input file. This is S, okay, yeah. Should be some defined here. Input file tables. Where is it? Oh, it's here. So this is 20 nanosecond stuff. But we are not going to write a script, but it's going to be a pro script. I might even have it. So control. I guess it's this way. MTPR. So this is going to be your sample input file you are going to use. So each is 20 nanoseconds. So in order to finish 1 microsecond MD, how many MD runs do we need to run? Huh?
Sorry, I didn't get it.
What?
I didn't understand what it is.
Okay, so we are going to run 1 microsecond MD simulation.
Okay.
Do we want to run just simple long 1 microsecond MD? We should separate.
We should separate.
Okay, so if each of the runs, so how long is this MD simulation that we define in the MD input file?
This one is 20 nanoseconds?
Yes, it is 20 nanoseconds because the number of steps we have is 10 million, but each of the time step is 2 femtoseconds. So 2 femtoseconds times 10 million is going to be 20 million femtoseconds. So 20 million femtosecond is equal to 20,000 picosecond, and 20,000 picosecond is 20 nanosecond. Does that make sense? You have to understand why this is 20.
I got it.
Not because I say 20 nanoseconds, because of these numbers. The NST limit is 10 million, ET is 0.001. You multiply it, that's going to give you the picosecond.
Yeah,
the picosecond is 1,000. Okay, so if this is 20 nanosecond, how many continuous runs do we need to do in order to cover 1 microsecond MD?
500,000.
1 microsecond is how many nanoseconds? 1 microsecond is how many nanoseconds?
1 micro. Is that 100 or 100? Sorry, 1,000. 1,000 divided.
1,000 nanosecond.
Yeah.
So
1,000
in order to cover 1,000 nanosecond and each is 20 nanoseconds, so how many runs do we need to do?
50?
50, yes. So we have to run 50 in the continuous MD runs, okay?
Yeah.
So how do we, so I probably have a production run somewhere. I can copy and give it to you. Let's see. So the production run is, the heating is still, running. So for the production run, let me see if I have an example that we can utilize. Okay, so this is my machine. Running camera. Okay, that's what I want to find. Okay, media. Where do I have an example? So I have something here. Oh, I see the problem. Yeah, it's not a problem. It's just that the system here is a little bit different than we had before. So I have a production, but this is implicit solvent. So it should be okay. We can, yeah, I think the general procedure is the same. So what I'm going to do is this. So this is a Perl script, okay? Alternate this and just copy paste this whole thing. This is your home directory. I will call it production run.pl. Okay, so here what this does is this. So we specify the program that we are going to use, which is pmemd.cuda. Initial run is 0 because we didn't start it. We will run 50 continuous run, so from I equal to 1 to 50. First read MD. So the logic behind this is that it will read the current directory and discover if there is any previous run. This is like, if there is anything happening in future, we can restart this and it will still work. So the C file is read, and then from that it's going to find exactly what the missing MD simulations are. So if JNew is equal, no, that's not correct. What we would like is this. If this is greater than 50, then just die. So the initial file, we are going to call it eq2.rst. It says that if it is the first time it is being run, this is my initial file, and the output file is going to be md_12345. Otherwise, go to the previous one. Okay, so pmemd mdn. So our file is prntop.new, right? So yes, this is what it's going to do. Old file, rst new run this, and we zip this. We don't need to zip this though. So if I look at the md.input file, I think this is correct. Okay, so this we have to change the mode to 755 for the production run so that we can run it. So if I again, let's look at here again last time. Okay, this is okay. This should be okay. So let's look at the eq2.output. Actually, let's not open it, but just look at the tail. I think it's okay. So it's very slow, honestly. 1 microsecond is going to take some time. Okay, so I will just give you an approximate number. So in 12 minutes, it finished on only 111,000 steps. So in order to cover 1 microsecond, which is 1 microsecond is 1,000 nanosecond. Another 3 is going to be picosecond. Another 3 is going to be steps. Okay. And the thing is that we use 2, okay, divided by this times 12 minutes, let's say. So this many minutes divided by 60 is hours, and divided by 24, okay, it's going to take a month. If I'm correct, it's going to take a month. In the HPC cluster, it will take faster. We can, start it. We don't need to actually fully finish 1 microsecond. Let's go back again. You have to understand what this whole thing is all about. Okay, so this AL5 is a simple system, right? What kind of a system is it? Like a regular duplex, right?
Yeah.
Okay, so even if you finish like just 1/4 of this 1 microsecond, which is going to be like a week or days or something like that, 7 to 10 days, we can still, analyze the data. We don't need to actually cover the whole month. Okay, if we need to, we can do it, but we are just trying to benchmark it. Okay, so it's not like something very serious. So this should be okay now. The only thing is that for the equilibration, so you watch out your Malakia Malatya account. Once this run EQ is done, which input file did we use? I can't remember. Okay, EQ to.input. And more. Okay. It's a million step. Okay. It is right now at it's right now at 135,000, so it's going to take like 8 times more time. Okay, so it's going to take like 12 minutes. So it's going to take like a couple of hours. Okay. Once it is done, I want you to run this production run. Okay, and it will run at the background in your Malatya machine. Is this clear?
Yeah.
Okay. So let's stop at this point. Okay.
So,
and we are going to meet next week. Yes.
When we run the script in background, all we have to do is type that and at the end of the code, or do we need to keep?
There are several ways. Yes, the end is basically the idea. But I'm going to give you an example. So you can do the following, like time, right? It gives you the time. Let me go to directory and maybe to TMP. The time, right? So if I time and it doesn't do anything. But if I do the following, time error, it will. Well, actually, it didn't work. Okay, because it is like a. So the best way will be the following. Okay, so this is going to actually put everything. So 2 greater than int1 is going to put all the output and the error message into this file. And then when you put this line, it's going to run at the background. So if we do this one, still it didn't actually do it. It's fine. Maybe that's not the best way. Maybe if I just echo deneme, so it types it, right? If I direct it to error, it will direct it to the error. But then if I put again this way, echo deneme error, it will do the same thing. But the thing is that if there is any error message, so here's the problem. If there is an error message, what might happen is that it might kill your job. You do not want to kill your job. So if there is an error message, just type it in the file I call error here. You can call it anything. And then when you put this 2 greater than int1 sign, you can even search this online. But what you want to do is this. Production run.pl, right? You're going to run that one. Normally you will have done this, right?
Yeah.
My suggestion is put it this way. Just like direct it to a file where I call it error, and then this. It doesn't fail. If it fails, it's not going to run. In this case, if it fails, it will still, run to the next step. It will go to the next step. It will not die the Perl script. Okay, any other questions?
So we can close the terminal when it's run in background, right?
Yes. Once you submit this one, you can close the terminal. But do not wait 1 week. Every day, just log into your account and check out if it's actually running or not. Check out if the files are created. Okay. So, for instance, a 10 million step is going to finish approximately. I'm just guessing. Okay. So, for the calibration, which is 2 nanoseconds, it will take 2 hours. So for a 20 nanosecond, it will take 20 hours. So every day you should have a file already created. Okay, so like, in one day, 1 or 2 files, MD output files will be created. So check it out. If you see something really weird, which happened before when we were running with, I guess, Ivan, that it was always creating the same file over and over again, because we made a mistake in the script. We realized it after a week, which was a pain in the neck. Like, all the runs were basically nonsense. Like, we lost everything. So it's always good practice to, check out your output files. Okay? Okay, I have to leave now, okay? So Any questions you have, send me or Kai or Amir, and they will help you. Okay.
Okay.
Okay. Take care.
Take care. Thank you.